Hello everyone, and welcome back to the speed of satellite in elliptical orbit. In the previous lecture we have learned that for example, if we have a circular orbit or circular path, so we derive that, for example, satellite revolving in such circular path, so the speed would be equal to capital G, gravitational constant, mass of the planet or the earth in this situation, and distance between these two bodies. So this was actually for the circular path, but in the real situation the satellites move around the planet in the elliptical orbit, not in the perfect circle. So this was an ideal case. For example, if we have a circular orbit, or we can say that, for example, r is, we have seen that r was radius of the earth plus height. So if height is very less, we can say, or approximately 0, we can say comparatively to the radius of the earth, the height is very small. So we can say that this equation can be written as the orbital speed, or we can say v will be equal to g m divided by re, or radius of the earth, and this is orbital speed of the satellite. But this is actually an ideal case. We can say that if there is such as Kepler's law, Kepler stated that all the satellites or planetary motion is actually in the elliptical orbit, and then it was Newton who gave the mathematical expression for this elliptical orbits. So we need to modify this equation because this is an ideal case, and the real situation or the realistic approach is we need to define the speed for the elliptical orbit. So if we have an ellipse, this is an ellipse, and we have a satellite, for example, this is the satellite in this case, like this one, for example, this is the satellite, and this is, let's say, the earth. Let's say I wrote it E, and I placed on a point on the circular on the elliptical orbit, and let's say I draw a line from here, or in axis, from here to that surface or that edge of the elliptical shape. This point is which is far away from the planet. Let's say this is the center of the circle. For example, I want to change the color, so let's say this is the center of the ellipse. This point, which is away from the planet Earth, this is called in the language of mathematics apogee. This is called apogee. Okay, and this point which is near to the planet, that is called perigee. Okay, this is called perigee. Now in the mathematics language, the center and the edge of the ellipse, this distance is called, let's say I want to change the color, let's say green color, so we can realize it. This is actually from here to, let's say here, this distance is actually a, and this is called semi-major axis, and the vertical distance is called semi-minor axis, but we don't need in this calculation. So simply we need some tricks to calculate the speed. So this is the semi-major axis, and this distance over here and this one, let's see, I want to, this is also semi-major axis. Let's say consider a distance from this center to the place where the planet is situated or is placed. This distance, let's say consider this is x. Now if I want to calculate this remaining distance, so this will be equal to, let's say, from here to here. If I want to calculate this, so this is just the distance a minus x. So the distance between the perigee point and the planet, that is represented by a minus x. Now if I want to calculate the distance from the planet to the apogee, so this distance will be equal to a plus x. For example, if I want to, let's say I want to represent by black color, let's say from here, okay, to this point. So here the distance is a plus x. So from this figure we have some ideas that, let's say we have a semi-major axis which is a, and we have a distance between the center and the planet, that is x, and we have a distance between the perigee and the planet, that is represented by a minus x, and we have a distance between apogee and the planet, that is represented by a plus x. Now it will make our calculation or derivation simple. Consider from this one, let's say now now consider the energy conservation at any point. Let's say consider the energy conservation. For example, so we have kinetic energy at any point plus potential energy at any point, that will be equal to, let's say we want to calculate this for the any point I considered for the perigee. Let's say I represent that is at P, and plus potential energy at perigee. So now if I put all the equation, so we have the kinetic energy half mv squared and plus the potential energy, that is gravitational potential energy, capital G, small m, capital M. Small m is for the satellite, capital M is for the Earth, and the distance between these two bodies, and this can be written as half m. Now the velocity of that satellite at point perigee, okay, so I will represent it with Bp, and plus gravitational potential, that is G m, capital M, divided by distance at perigee, okay, at point P. So now if we simplified it, so this m will be cancelled out from both sides of the equation. Now we can say that v squared divided by 2 minus g m divided by r, and that is equal to vp squared divided by 2 and minus g capital M divided by rp. Now let's say we call it this equation number 1, okay. Now again consider the energy conservation at both points, apogee and perigee. So again consider, these are the tricks to calculate this speed of the satellite. So let's say we have the kinetic energy at apogee. Let's say I represent that with A, and plus potential energy at A, that will be equal to, according to the conservation of energy, that will be equal to kinetic energy at perigee plus potential energy at perigee. So we can now go through the calculation. So we can say that half mVA, because this is at apogee, so we can say half mVA square minus G small m capital M divided by, now the distance is RA, that is equal to half m, now this is Vp square minus G small m capital M, now the distance is at point RP. Now by crossing this small m, so we can say that half Va square minus G m divided by Ra, that is equal to Vp square divided by 2, or half you can say, minus G m divided by Rp. This is, let's say, equation number 2. Now consider the conservation of angular momentum. Okay, now consider the conservation of angular momentum. So angular momentum at apogee will be equal to angular momentum at perigee, and we can say that angular momentum at P, that is mass of the satellite, and Vp Rp, we know that this is the equation for the angular momentum, and M Va Ra, let's say we M and M will be cancelled out, so we can say that VA, we can calculate VA from this equation, that will be equal to Vp Rp and divided by Ra. Let's say we call it, this is equation number 3. Now put equation number 3 in 2, so we can get half VA is now Vp Rp divided by Ra. Now this is replaced with this, and minus G capital M divided by Ra. Okay, that will be equal to Vp squared divided by 2 minus G capital M divided by Rp. Okay, now calculate this, or we can simplify it with this equation. Let's see, now by simplifying, we can get this equation in this form. For example, this will be equal to R Vp squared Rp squared divided by 2Ra squared Vp. Now replace or just transfer the Vp on one side and Gm divided by R on the other side. So this will be equal to 2, and that is equal to Gm divided by Ra and minus Gm divided by Rp. Okay, now by calculating this equation, we can say, by simplifying this, we can calculate that Vp square will be equal to 2gm into 1 over Ra minus 1 over Rp, okay, and multiply by Ra square divided by Rp square minus Ra square. Okay, so this will be multiplied with each other. Now let's say we want to make it more simple, so we can say that 2gm into, let's say, taking LCM of this, so this will be Rp, and this will be Rp minus Ra, okay, and this can be written as Ra squared divided by Rp minus Ra into Rp minus Ra, just a formula a minus a square minus b square. So here if we can cancel out this one, oh sorry, one is plus, okay here, and 1r will be cancelled out with this one. So by simplifying this equation, we can say that this will be equal to 2gm is square actually, and this is Ra divided by, let's say, whole divided by Rp into Rp plus Ra. Okay, this is the final equation. Now we can put all the values over here. So let's say I want to put all the equation, as we know that Ra is the distance of apogee, which was a plus x, and Rp was the distance of the perigee, which was a minus x from the figure. So by placing that in that equation, we will be equal to Vp square will be equal to, in the final version, we can say this will be Gm divided by, okay, a into a plus x divided by a minus x. This will be actually the Vp or the speed at perigee. Now let's say we put this in equation 1, because our target is to find out the speed of the satellite in elliptical orbit, not at the perigee. We can discuss this later. So put in equation number 1. If we recall equation number 1, so it was v squared divided by 2 minus gm divided by r equal to Vp squared divided by 2 minus gm divided by Rp. So 1 will implies v square divided by 2 minus gm, okay, and divided by r, that will be equal to, now Vp square is actually this equation, so we can say this is gm divided by 2a, and this is a plus x divided by a minus x, so n minus g m divided by Rp. Now Rp is actually equal to a minus x. From here you can say, from here Rp is actually a minus x. Now rearranging these equation, So we can say now by rearranging these values. So let's say, oh, what happened, sorry, let's say now v square divided by 2 minus gm divided by r, that will be equal to let's say take an LCM, that is 2a into a minus x. This is the LCM. So the this will be actually g, take g as a let's say common, gm. Okay, so it will be easy for us. Now this will be a plus x, okay, and minus 2a, okay, by taking LCM. It's very simple. Now by calculating that and taking negative common, let's say this will be v square divided by 2 minus gm divided by r, that will be equal to, in final version, taking negative common from that equation, or you can say, okay, let's calculate x minus a and divided by 2a into a minus x. Now this is x minus a and this is a minus x, so we can take negative from the above common. So if I take it, gm, this will be a minus x divided by 2a into a minus x. Now this will be cancelled out, so we can say that v squared will divided by 2 minus gm divided by r, that will be equal to minus gm divided by 2a. Okay, now if I okay, now if we sorry, okay, this will be, now by taking this one, this will be, let's say, more simplified, okay, to this will be equal to gm divided by r minus gm divided by 2a. Okay, now okay, now cross multiply by 2, this will be equal to 2gm divided by r and minus gm divided by a. Now taking square root, it will be equal to v is equal to 2gm divided by r and minus gm divided by r, a and square root. Now this is our final equation. Now this equation tells us the exact situation, that for example, if we have an elliptical shape or elliptical path and the satellite move in the elliptical orbit, so we have this exact equation, and this is the exact equation we need. Now for example, if we want to say that let's say we have our, now if a is any arbitrary point r, let's say this is this a, let's say, goes to r, any arbitrary point r, so this equation will be automatically becomes for the circular orbit gm divided by r, sorry, not 2, there is no 2. Okay, let's see, this will be equal to, sorry, this will be equal to 2gm divided by r and minus gm divided by r and square root. So this will be again for what? Gm divided by r, and that is actually the circular orbit. So this is the real equation which can be used for any elliptical orbiting speed. It's a little bit lengthy video, but I was concerned about the derivation, and thank you so much for waiting. And if you have any question, let me know in the comments box. See you again.